back. Today we're going to talk about multiple angle identities. So I've got my notes up here. I'm actually scrolling down to the bottom because I'm going to have you add something to your formulas sheet. So you've got this formulas sheet, and we're going to add 3 formulas, and they're going to go underneath the heading, what am I going to call them? Power reducing identities. So now on your sheet, power reducing identities. So part of the thing that's happening right now is we're getting to the point where we have a lot of formulas. It can be difficult to discern like which one am I supposed to use. And a lot of these are going to look somewhat similar, so that sheet is going to be important. So power reducing identities, we've got 3 of them. We're going to put in sine squared u is equal to 1 minus cosine of 2u over 2. And cosine squared u is equal to 1 plus the cosine of 2u. So it was minus up here, it's plus down here, over 2. And the tangent squared of u is equal to sine over cosine, so it's going to be 1 minus cosine of 2u over 1 plus the cosine of 2u. Now, you're probably thinking, or maybe you are, or maybe you'll get to this point where you're like, I wonder about that. How do I know if I'm going to use a Pythagorean identity for the sine squared or one of these? Well, in general, Pythagorean identities are better. So normally I'm not going to sub out a sine squared u for a 1 minus cosine 2u over 2. It's just not, I mean, that is a hard substitution because it actually makes it more complicated. However, if you're evaluating your proof and you see that your sides, one of them has this sine squared u, and you're trying to make it more complicated, you're trying to make it a fraction, you're trying to incorporate a double angle, like right here, this cosine of 2u is cosine of a double angle, meaning 2 times u, you might consider it, okay? So it's not necessarily going to be your first knee-jerk reaction to say, oh man, I got to substitute, it's 1 minus cosine 2u over 2. But if you're trying to make it look more complicated, if you're trying to incorporate a fraction, if you're trying to put in a double angle, it could work. And we're going to look at some strategies here. We're going to do about 5 problems here and use some of these formulas. Now, you're going to recognize some of these steps. And in this section, we're specifically kind of working on some formulas that are going to allow us to take it like one step further. So let's look. One of the important things about multiple angle identities, they're based on adding sometimes. Okay, so sine of 2u is actually equal to sine of u plus u. Okay, and so if you think about it like that, it makes sense with last section, because last section we had, cosine of a plus b, or sine of u minus v, and we could put this formula together. Well, a double angle is really just based on that. So I'm actually going to play on that principle in this one, and I see the sine of 2u, and I'm actually going to write this as the sine of u plus u. And what I'm going to do is I am going to use my angle sum and difference formulas here, right? So the sine of u plus u is equal to the sine of u times the cosine of u. Now, if it helps, you can do like this, like u sub 1, u sub 2. They're actually the same. But in this case, if you want to help keep track of them, so this is like u sub 1, u sub 2, right? And then I would do like a plus, because for sine they match. And then I'm going to do the cosine of u times the sine of u. And if it helps, you can sort of do it like this. But really, ultimately, they're the same. But if you need help keeping track, maybe you don't. I don't know. Maybe I'm overcomplicating this. But essentially, they're all the same. They're not really like this, but that's essentially what it looks like. But if I rewrite this as sine of u cosine of u plus, and I can change this around the commutative property, so sine of u cosine of u, it's really equal to 2 sine of u cosine of u. Well, check it out. What do I want it to be equal to? I want it to be equal to that. So my last line is 2 sine of u cosine of u. So my strategy here was to take a double angle formula and make it into an angle addition formula. Okay. All right. prove the identity. Now this one looks like something we've done before, right? And so I told you kind of like if you see a 4, like to the 4th power, cosine to the 4th power, sine to the 4th power, kind of be thinking about, could I use a difference of squares here? So I've got two sides. I've got a double angle of cosine here, cosine of a double angle, and then I've got a difference of 2 squares over here. So which side's more complicated? Well, I've got this over here, which is pretty complicated, so I'm going to do this. Cosine squared u, and it's actually x. Let's keep that continuous. Minus sine squared x. And then I've got cosine squared x plus sine squared x. All right, so hopefully you sort of at this point recognize that this is 1, right? So I've got cosine squared x minus sine squared x. This doesn't look like a whole lot. In fact, I think we've actually in this chapter done a proof where this was the end goal. Well, now we're sort of to this point where we are taking it one step further. So just take a look here. I want this to be equal to the cosine of 2u. So just look for a second at the cosine of a double angle here. And you'll notice that our double angle formulas, okay, there's 3 of them. Actually, the cosine of 2u, or 2 theta, can be equal to one of 2 things. Either it's cosine squared x minus sine squared x, or 2 cosine squared x minus 1, or 1 minus 2 sine squared x. Okay, so what does this mean? Cosine for this double angle cosine is a little bit tricky. It's got 3 forms. Well, we'll just take a look for a second. Which one does this look most like? Well, it's an identity right here. So this is actually this, right? And so that's a straight up substitution right there, and that's literally one of the forms of the cosine of the double angle. And so I can say cosine of 2x is equal to the cosine of 2x. Okay, that's a sub out. So for cosine, if you have a double angle, cosine of 2 theta, 2x, 2u, there's 3 different forms. You're going to kind of have to navigate that and see which form would be most useful. All right, let's do this one. Next one. Solve algebraically in the interval of 0 to 2 pi, sine of 2x is equal to the cosine of x. So when I'm solving, I obviously want to have all variables on same side. So sine of 2x minus cosine x is equal to 0. So obviously, I can't do anything with this. Like I can't subtract them. I don't really know what I'm doing. So I'm going to try to work on switching out one of them to combine some like terms, things like that. So we're in the section on double angles. So I'm going to work with this double angle. If you didn't know what to do, again, take the most complicated piece. So the sine of 2u is 2 sine x cosine x minus cosine x. So this was an identity right here. This is a double angle identity. And so what do you see now? Now I have 2 terms, so 2 sine x cosine x minus cosine x. So I'm going to factor out a cosine x. So cosine x times 2 sine x minus 1 equals 0. Well, what do I do with this? Anytime something is equal to 0, I can factor it and set the pieces equal to 0. So either the cosine of x is equal to 0, or 2 sine x minus 1 is equal to 0. So either cosine x is equal to 0, or this would be plus 1, and then 2 sine x equals 1 over 2, or sine of x is equal to 1/2. So think about it like this. If I'm looking at my unit circle, and I'm on the unit circle 0 to 2 pi, I want to know where the cosine is equal to 1/2. And remember, this is cosine x sine x for my coordinates. So I want where my x value equals 0 and where my y value is equal to 1/2. So x value equals 0 here and here, because this would be 0 comma 1, and this would be 0 comma negative 1. So that's pi over 2 and 3 pi over 2. So that's my solutions here. So cosine of 0, cosine of x equals 0 at 3 pi over 2 or pi over 2. And where is my sine value equal to a half? So that would be, my y value is a half, so it's going to be here, which means that this is a 30-degree angle. So this is pi over 6, because this would be the half, right? And over on this side, this would be a half for my y value. So this would be 5 pi over 6. And so I've got pi over 6 and 5 pi over 6 as well. Don't need to account for a 2n pi or anything like that because I'm in the interval 0 to 2 pi. Okay, so those are my 4 answers there. Just solve that equation, put everything equal to 0, and then factor out like we've been doing. All right, here we go. Sine squared is equal to 2 sine squared x over 2. So I've got this fairly complicated looking side here, right? I've got a sine squared, but also an x over 2. So let's see if we can work with that. What would it be equal to? 2 sine squared x over 2. So just take a look at what our formulas we have here. And I've got sine squared of x over 2. So I'm going to look at my ones that I just added, my power reducing identities. Okay, because with my power reducing identities, what I can do is I can take it and I can make it into sine squared would be 1 minus the cosine of 2u over 2, and in this case my u is x over 2, so this would be 2 times 1 minus the cosine of 2 times x over 2, right? And then over 2, and so this is a little bit of pre-work here. 1 minus the cosine of x over 2, and so then these eliminate because it's times 2 and then divided by 2. And so I've got sine squared x is equal to 1 minus cosine x. Right? So 1 minus cosine x. How did I know to do that? Well, I played on one of the identities that I had. Right? I played on one of these power reducing identities where I had a sine squared x. And so what's it equal to? So here we go. So I've got this sine squared x equals 1 minus cosine x, and I'm trying to solve, right? So I need all my variables on one side, and so what I'm going to do is I'm going to say sine squared x minus 1, so I'm subtracting 1, and then plus cosine x is equal to 0. So now I've got a bunch of stuff here. I've got a sine squared x, I've got a 1, I got a cosine x. I would love for everything to be all in terms of the same trig ratio. So what I'm going to do is I'm going to convert my sine squared x to a 1 minus cosine squared x. How would you know to do that? Well, as you get exposure to this, understand what I just did there. I had sines and cosines, squares and not squares, and so I just took it all, so it's all in terms of cosine. Well, in the previous problem up here, look what I did. So in the previous problem up here, I made it so I could factor out a cosine, right? So I had 2 sine x cosine x minus cosine x. Made it so I could factor out a cosine. Well, if I have everything in terms of cosine, I can factor some things out, factor out a cosine. Also, I told you, you know, these identities that we're using, Pythagorean is still the best. They're still the best. You still want to take them and use those to convert more often than not, as opposed to going from like a sine squared x to, you know, I wouldn't necessarily, it would work, but I wouldn't want to go to one of the, 1 minus cosine of 2 u over 2. Like that's not a good swap out. Pythagoreans are still good swap outs because what I'm doing is I'm making them, they're still simple, right? So look at what happens here. I got a 1 and I got a minus 1. Those cancel out. So now I have minus cosine squared x plus cosine x is equal to 0. So if I rewrite, I've got cosine x minus cosine squared x equals 0. Factor out a cosine. 1 minus cosine x equals 0. And now we're kind of back to a point where we were before, right? In the problem before, we're getting to a point where we've got something we can factor. And so either cosine x is equal to 0 or 1 minus cosine x is equal to 0, which would mean that cosine x is equal to 1. So my x coordinate on my unit circle is either 0 or 1. So here, 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 and here. So let's see. I just need to solve. So I've either got 0, pi over 2, pi, or 3 pi over 2. And any of these are plus 2n pi, right? So I need where n is equal to 1, 2, 3, etc., because all of my angles I could go around again. So where cosine is equal to 0, that's where my x value is equal to 0. So that's pi over 2 and 3 pi over 2, or where my y value is equal to 1. So that would, or my x value is equal to 1, which would be at here and here. Well, this is, so my pi value, actually this is 0, negative 1. So it wouldn't be pi. I made a little mistake there. So this isn't plus or minus 1, it's just 1. So this is 0, 1 here. So it's actually, my answers are these three spots right there. And this answer reflects that. Okay? All right, one more, just one more. And I'm not trying to breeze through these, but you know, just exposure to these strategies and looking at some of the things that are even possible to do can kind of get you in the mode of thinking about strategies and how can I manipulate these equations. All right, so I've got two sides here. And one of the more difficult parts about when you get into these multiple angle identities is which side do I pick? So for me, what I have become accustomed to, I've been doing this for a while, and I hope that you can kind of start to see this one is more complicated, but this one has room for expansion, right? What do I mean by room for expansion? Well, cosine of 3x can really be written as the cosine of 2x plus x. And the cosine of 2x plus x can be written as cosine of 2x times cosine of x minus sine of 2x sine of x. And so recognizing multiple angle identities, cosine of 3x, cosine of 4x, cosine of 2x, can change it from a multiplication problem, 3x, to an addition problem. See how that's helpful in this one? Because I know in my answer I'm going to need to have a subtraction problem. I can use a multiple angle identity to change from one to the other. And at the very end of the day, just try something. Try something. Okay? So now I need a cosine 3x. I have a cosine cubed x. I have a cosine of 2x. So look up here. I wrote them down. My double angle identities. It's kind of messy there, so I'll show you here. Double angle identities. So my cosine of 2 theta has 3 forms. Well, which one am I going to use? I know I need a cosine cubed. So I'm not going to use the one that says 1 minus 2 sine squared x. I'm actually going to use this one. 2 cosine squared x minus 1 times cosine of x minus, now I've got the sine of 2x, and what am I going to do with that? So I'm going to convert that. Let's see. I need cosine of x, so I'm going to use 2 sine x cosine x times sine x. So on my sheet, sine of 2x is this. That's a sub out. Cosine of 2x is this. That's a sub out. Let's distribute this in. 2 cosine cubed x minus cosine x minus 2 sine squared x cosine x. So what happens here? So I've got two things going on here, and I need to prove that it's equal to this identity. All right, so what we've got is 2 cosine cubed x minus cosine x minus 2 sine squared x cosine x. Well, when we look at what we're going toward all cosines, and so I'm looking at this guy here, and I'm thinking to myself, okay, I got to get a swap out. And if I remember that cosine squared x plus sine squared x is equal to 1, that's a Pythagorean identity, then sine squared x is equal to 1 minus cosine squared x. So I'm going to sub that out because I want all cosines. So 2 cosine cubed x minus cosine x minus 2 times, and this is going to be, so sine squared x is 1 minus cosine squared x times cosine x, right? So I'm still working here. Cosine cubed x minus cosine x. And inside my brackets here, I have, when I distribute this, so cosine x minus cosine cubed x, because cosine x times 1 is cosine x times cosine squared x. And then I'm going to distribute the 2, minus 2 cosine x, plus, so this is minus, so it'd be minus 2 times, so plus 2 cosine cubed x. Combine like terms. So here's 2 cosine cubed, here's 2 cosine cubed, so I have 4 cosine cubed x, and then minus 3 cosine x. And that's what I want it to be equal to, right? Okay, so what did I do? I used angle sum formula. I used an angle sum formula to break up a cosine 3x. You're going to do that with cosine 4x. You're going to do that with cosine 5x. Then I subbed out a cosine 2x for x's. So in general, I want to go from cosines of 3x's to 2x's to just cosines and sines of x's. Then I got down here. So that was me subbing out double angles. So sub out multiple angles. Right? So don't have cosine 3x's, don't have sine 2x's. Sub those out, okay? Then you get down to a point where you've got sines and cosines mixed. Try to go all to 1, which is what I did. I tried to go to all cosines because my answer had all cosines. I'm going to circle this a couple more times. That's a joke. And then I was able to combine like terms, okay? Stick with this, guys, and hang in there. If you have any questions, please let me know. Thanks for watching, and we'll see you next time.